Hello. Today's topic is integrals as general equations and particular solutions. So as you can see, we have an equation here. dy over dx is equal to f of x, comma, f of y. This just means that the equation of dy over dx has terms both in terms of x and terms of y. An example of this would just be something saying like dy over dx equals 2x plus 3y. Now, to be able to solve an equation like this, we will take this example right here. dy over dx equals cosine of x. Now, what we first need to do is we need to isolate the x terms with the x terms and the y terms with the y terms if there's multiple y terms. So first, we can say that this side right here is being multiplied, is being divided by a dx. So to isolate the dy, we can multiply both sides by a dx, which cancels a dx here and adds a dx here. So that should look something like dy equals cosine of x dx. Now, to solve this equation, we have to integrate both sides. Now this right here will give us y, and we can say y is a function of x. It's the same thing as saying f of x, except I prefer to write y of x instead of f of x. So y of x equals negative sine of x plus c. We cannot forget that c. Now, say that our example stated that our initial condition was y, when you put in a 0 in for x, is equal to 2. Now, we take this equation y of x is equal to negative sine of x plus c, and we substitute in a 0 every time we see an x. So, and this will give us the answer 2. So negative sine 0 plus c equals 2. Sine of 0 on a unit circle, say this is a unit circle, well, not a unit circle, but this is half a circle. Here is where 0 is. This right here is just 1 comma 0. This right here is cosine, and your y value is sine. As you can see, sine is equal to 0. So sine of 0 is 0. So we just say 0 plus c equals 2. We can simplify this further by saying c is equal to 2. Now, this equation right here is what you call a general solution, because we have general terms as in c. Now, when you take the equation and you substitute in your variable with a constant, it is now called a particular solution. I just simply abbreviate solution instead of writing it out. I just write SOL apostrophe N. Now that is it for example 1. Now, for example 2, we are given a bit of a more complex problem. So we have y double prime x equals x plus 2. Y of no prime, or essentially just the original equation, when you plug in a 1 equals 1. And finally, oh well, I could just write y prime 1 equals 1. That way we can just keep the pattern of decreasing derivatives taken. Let me space this out a little bit. Now, we're given this equation in the beginning. So simply we can just write y double prime of x equals x plus 2. Now we integrate both sides. This gives us on the left side y prime, this time a single prime, equals, and for here, we integrate in terms of x. So we have x plus 2. We do basic integration, so it gives us x squared over 2 plus 2x. We are given the initial equation over here stating that when you plug in a 1 for x, your whole equation will be equal to 1. So let's try that. Oh, my mistake. It wasn't equal to 1. It was equal to 0 in the initial values. All right. So we plug in a 1 and it gives us 0. Now, as you can see, I forgot a very important part, and that is the plus c. It is very easy to forget when you're integrating because it is something that you don't really consider. All right. We have x squared over 2 plus 2x plus c. Now we want to differentiate this c from a future c that's upcoming once we integrate again. So what we call this c? C1. Now for every x we see on this equation, we will plug in a 1. So 1 over 2 plus 2 plus c1 equals 0. If we simplify this down, we find that c1 is equal to negative 5 over 2. Now we substitute this negative 5 over 2 back into this equation, and that'll give us yx single prime equals x squared over 2 plus 2x minus 5 over 2. Now, we are given that there's a double prime here, so we have to integrate 2 times. So when we get this equation right here, we integrate one more time. Integrate. We integrate in terms of dx. Now this brings us y of x. Now integrate normally. So x to the third. Now divide by the new exponent. So 3 times 2 is 6 plus 2x squared over 2, which simplifies down to just x squared minus 5 over 2x plus c2. Now that we have this equation right here, well, let me move it over here. Now that we have this equation right here, we can look at what our initial condition was. So whenever we have a yx function, when we plug in a 1, we get a 1 in return. So let's go over here. Let's rewrite that 1 equals 1. All right, so when we plug in a 1, it'll give us 1. So let's just rewrite this equation. Y1 equals 1 over 6 plus 1 minus 5 over 2 plus c2 equals 1. when you put this example in the calculator, or when you put this equation in the calculator, it brings back C2 equals 7/3. We'll just double check. 1/6 plus 1 minus 5 divided by 2 minus 1. Yep. Gives us 7/3. All right, now once we have that, we can finally get our particular solution for the total equation. And now this is our new particular solution. Now lastly, for example 3, oh no. For example 3, I will have to bring in an equation or not an equation, a word problem, which states the following. A lunar lander is falling freely towards the surface of the moon at a speed of 450 meters per second. Its retro rockets, when fired, provide a constant deceleration rate of 2.5 meters per second squared. The gravitational, this just basically says that neglect the moon's gravitational, well, not neglect it, but that's what you need to counteract the acceleration. At what height above the lunar surface should the retro rockets be activated to ensure a soft touchdown, meaning final velocity equals 0 at impact. So what do we know from this equation? From this word problem. So we know that our initial velocity, which we call v naught, is negative 450 meters per second. I say negative 450 because it is heading towards the ground. It is going down. But velocity in and of itself is always positive because it's always magnitude. So we have a 450 meters per second velocity and an acceleration, or acceleration of 2.50 meters per second squared. And we want our final velocity, which we will call Vf, to equal 0. We will have a Vf squared equals V naught squared plus 2 delta XA. This right here is one of the kinematic equations, and we will bring another one in, which states Vf equals AT plus V naught. Now that we have this information right here, we can plug in for our values. Let me just move this over. All right. So our final velocity is equal to 0. And our initial velocity is equal to 450, negative 450 squared, plus 2 times the acceleration, which is 2.5? Yep, 2.5 times delta x. We're trying to find delta x because we're trying to find what height above the lunar surface we want to deploy the rockets. So that'll be our delta x. Now we can just say 450 squared over 2 times 2.5 is equal to our delta x. If you put this in a calculator, it gives you 40,500 meters, which is the same thing as saying 40.50 kilometers. Now, we want to figure out at what time we should, what does it say? Well, here we say what height, but we can also find at what time we should, how long it would take. Wait. Yes, how long it will take to completely decelerate the the spacecraft. So for that, we will use this equation right here. The equation states final velocity is equal to acceleration multiplied by time and then adding our initial velocity. So for this one, we have our final velocity, we want it to be zero, meaning that our touchdown speed will be zero, ensuring a soft landing. Now our acceleration is 2.5, and we multiply by time and we subtract 450 because that's what our acceleration is, our initial acceleration is. So we have 450 is equal to 2.5 t. Now we're trying to solve for t. Now t, if you put it in a calculator, should give you 180. So the time it'll take you to completely slow down the rocket ship, the spacecraft to 0 meters per second, coming in at 450 meters per second, and you're decelerating it at a rate of 2.5 meters per second squared, it will take you approximately 180 seconds to successfully complete that deceleration. Thank you for watching the video. See you another day.